Hello everyone, I'm Jaegal Chu, one of the instructors of this course. So this is a 14th week and we continue to study deep learning, especially focusing on the topic of recurrent neural networks. The objectives of this week's lecture is to understand recurrent neural networks, and also it's a simple applications in character level language models, and also how to train this RNN model. And this is the basic structure of a recurrent neural networks. It basically takes an input as a sequence of some data, and then the same network module is applied over and over on each input at different time steps. And in terms of basic input-output setting, one particular module of an RNNs will take an input of xt at the current time step, as well as the hidden state output from the previous time step. And then using them as an input, it computes the new hidden state. In general, this current time step's hidden state vector is computed in this form, where we transform the previous time step's hidden state vector transformed by our linear transformation matrix W, H, and H. So this H is indicating HT minus 1, and this is HT. So this is transforming the previous hidden states into the current hidden state, and then also we take the input as the current time steps input, and then it is transformed by this linear transformation where X is transformed into HT, and then altogether they are added up, and then this added output is going through this tan H as a nonlinear unit, and this tan H nonlinear unit will have this kind of shape where the minimum and maximum value is specified as 1, and obtaining this HT, which ranges from -1 to 1, and then it is transferred to the next time steps RNN module, and also it is also used as a input to generate this output vector at the current time step, which is a YT. And then the transformation used here is defined by this linear transformation of W, H to Y. So this is HT and this is YT. This is how the original or vanilla RNN works in general. And in terms of input and output settings, RNN can be categorized into several different problem settings. So suppose we are given this vanilla neural networks where we have input and output, and then we have some neural network modules that transforms the input to output. So in this case, there is no notion of time steps or sequence information. But when considering this RNN setting, where the input or output are a sequence of some information, in this case, we take the input as a single time step input, and then it goes through the same RNN module, and at the same time, it will generate the output at every time step. So for example, given a particular image, if it generates a sequence of words that explains this image, and then this word is generated one by one at each time step. And then the next case is this many-to-one case. So in this case, the input is sequence, and then they will be processed by our RNN module to generate the single output at the end. So the output doesn't have any sequence information or nature, but only the input has such sequential nature. So for example, in this case, we can take the sequence of words, and then decide whether this sequence of words indicates a positive or negative sentiment. So for example, given this input, then it will take the input as I and love and this and movie and so on at every time step. And then at the end, it will generate the label of positive sentiment. And if the input sequence changes in this form, and then at the end, it will generate a single output of a negative sentiment. The third case is a many-to-many setting, and in this case, we can imagine the case of taking the input as a sequence of words and then generating another sequence of words. So one representative example corresponding to this problem setting is machine translation. So we give a sequence of words in one particular language here, and then it will generate the sequence of another words in different language. Lastly, this problem is also many-to-many setting, but in this case, the outputs should be generated at the same time given a particular input at each time step. So in this case, the difference from the previous case is that it doesn't allow any delay in generating our output, and thus in this case the real-time aspect is important, such as this video classification tasks on a frame level. Next, let's look at some simple and interesting application of this RNN model in the character level language model. So the language model is some model that can predict the next word or next character given the previous sequence of words or characters. So for example, let's just train the character level sequence of HEELLO, and in this case the vocabulary or the unique characters that we can find from this data can be viewed as this HELO as 4 unique characters, and then those vectors or those input can be encoded by this something called one-hot vector, where we have the total number of dimensions as the number of dictionary size, and then each corresponding character will set the corresponding dimension as 1, but all the other dimensions will be set as 0. So these are the 4 inputs as we go through the sequence of this HELLO, and then each of these input vectors will be given to our RNN module at each time step, and then it will generate this hidden state vector, and in particular at this time step it will take as an input this hidden state vector from the previous time step, and then it will be transformed by this linear transformation matrix, and then also the current time steps input will be also transformed by this matrix, and then those transformed outputs from here to here will be added together to generate the current time step. And then this current time steps hidden state vector will be further transformed by our nonlinear transformation by using 10H function, and then that hidden state output vector will be further transformed by this transformation to generate our output vector here. And then this process is done at each time step to generate our output vector at every different time step. This output vector is further transformed by the softmax function. This softmax function transforms each of our elements in the output vector by using this transformation. So in this case of first entry, we will transform it to e to the power of 1.1 and e to the power of 2.2 for this, and so on. And then we just sum them up. So we have two more entries, and then we divide each of this value. So for example, e to the power of 1.0 divided by this value, and then assign it as the first element in the resulting vector. And then we do the same thing on the second element, and instead of using this, we use this value to generate this second element in the resulting vector. And that way, this vector will always sum up to 1, which can be interpreted as some probability distribution over 4 different elements in our output vector. And this 4-dimensional output is actually corresponding to our dictionaries. So we have the 4 elements in our dictionary of H, E, L, and 0001 as O. And in this example, we basically pick up the index that has the largest element value in our probability distribution vector, which was generated by this softmax function. And then we would pick up this E because that is the corresponding character in our dictionary, and thus this one will be our output. And then this generated output will be used as the input at the next time step, and through this process we continuously predict or generate the next coming character in this model. So this is the character level language model that can predict the next character given the previous sequence of characters. And this was done by this recurrent neural network or RNN module. So this character level language model can be applied to any types of paragraphs or larger text. For example, let's train our language model using Shakespeare's Sonnet 116, which has this kind of paragraph. And we train our RNN module based on this character level language model. And then at the initial stages of training, this is the generated character sequences, which doesn't make much sense. But as we train more and more, the generated character sequences looks like a real kind of paragraph based on our training data. And after all, it generates this really nice looking character sequences. Our character level language model based on RNNs can even generate the thesis, which generates this kind of a academic looking article. It can also generate the programming code, where this example is generated C code by this RNN model. And let's think about how to train our recurrent neural network model. So given this sequence of an input, what we do here is that given these kind of a sequence, and then suppose our RNN module generated maybe L and O and H and so on. But these output should be E, L, L and so on, which is the correct next character. And then from the differences between these, the errors will be generated, and these errors will be backpropagated to train our neural network parameters. So altogether, the loss is computed at each time step where we compare the generated output and also the target output. And then the loss generated at each time step will be backpropagated by following the reverse direction of this network directions. So the backpropagation is done through the time sequence, and so the loss will be going through here, and then going through here, and going through here, and so on. So this part will contribute to training all the parts of the entire sequence. But in practice, we do not follow this kind of training the entire sequence, but we instead use this truncated backpropagation through time. So what we do is to run forward and backward through only a chunk of sequence. So given the entire sequence, we just cut them into a piece, and then we start from here and then compute the loss, and then the loss is only used to train within this finite length of sequence. And then moving on to the next chunk, and then we compare our output with the target variable, and then generate the loss, and then train our model within this chunk of sequence. In this manner, we train our RNN module by using only a sequence of finite lengths, and this is called a truncated backpropagation through time. In summary, we studied recurrent neural networks and also discussed some interesting application called character level language model. And in the last part, we discussed how to train our RNN module. And in the next lecture, we will study a more advanced architecture in this RNN, which is called a long short-term memory. Thank you very much.